One of the key tenets of DevOps is making it easy for software developers to get their code into production quickly and safely. For a lot of companies, AWS is a key part of implementing that. But getting started with AWS can be overwhelming. There are currently over 200 AWS services, and many of those have multiple components wrapped in a single service. It's a lot like wanting to learn to drive a car, and I start you off by explaining that the carburetor mixes the air and the fuel, then injects it into the cylinder where the piston compresses the mixture. Then a spark plug ignites that, resulting in an explosion that forces the piston back down, translating chemical energy into mechanical energy that ultimately forces the wheels to rotate. And meanwhile, you're thinking,
Dude, I just want to go to 7-Eleven for a Slurpee.
No way, buddy. No fucking way. You cannot use the double gulp cup for the fucking Slurpee. This right here. This is Slurpee cup.
So in this video, I'm going to introduce you to the main components that you'll use in AWS every day, explain to you what role they play in building a scalable app, and how they integrate into the overall DevOps lifecycle. I'm also going to talk about a few non-AWS tools that you're definitely going to want to know. I know, talking about non-AWS tools and services is heresy, and Bezos will probably unsubscribe from this channel after hearing me say that, but I think it's that important for you to learn. So let's get started, and for reference, I'll put links to the different sections in the description down below so you can jump around as you need to. If you're new here, I'm Will Button. This is DevOps for Developers, where I talk about implementing DevOps in modern software engineering, whether you're new to DevOps, new to software engineering, or new to technology in general. So like I mentioned in the intro, there are over 200 AWS services, but you don't need to know them all. There are a few services you'll use every day, and the rest, just worry about learning those when you need them. So here are the common AWS services that you must know. We'll start with compute, and compute comes in two main flavors, EC2 instances and containers. You'll use both, though I would encourage you to favor containers over EC2 instances unless you have proof that you need to do otherwise. Containers are just easier to update, manage, deploy, and scale. And since we're talking about containers, that means you're going to need to know Docker as well. So if you're not already familiar with Docker, add that to your list. I've got a fairly in-depth video on it right here. One thing worth pointing out is EC2 instances and containers in AWS are protected with a firewall, for lack of a better term. It's called a security group, and this allows you to control what traffic is allowed in and out of your compute instances at the network level. When it comes to containers in AWS, you have a few different options. ECS, the Elastic Container Service, EKS, the Managed Kubernetes Service, and Fargate, a completely managed solution. Just go with Fargate and you can thank me later. And then there's this thing that's not really a compute thing, but you'll find it in the compute section of AWS, and that's load balancers. Load balancers do just what the name implies. They balance the load across multiple destinations. These destinations can be EC2 instances, containers, or even other load balancers. The important thing is that you use them always. Never expose anything in AWS to the internet except a load balancer. The reason is that load balancers let you swap the backend destinations without affecting the endpoint that your users see. For example, if a server crashes and needs to be replaced, they also let you scale up and down. So if you need more capacity for your application, you just add additional servers to the load balancer and it will put them to work. But the most important reason, in my opinion, is it's built to handle DDoS attacks. So it can withstand the onslaught of traffic and keep responding, something that your EC2 instances or your containers can't do. The next thing we'll talk about is a VPC, and that stands for Virtual Private Cloud. And it's AWS's way of providing you with your own private network inside of AWS. This is important for a couple of different reasons. First of all, every script kiddie on the internet knows all of AWS's IP addresses by heart, and they relentlessly beat on them every minute of every day looking for someone who's left a port or an IP address unsecured. VPCs help eliminate that by not exposing anything to the internet unless you tell it to do so. VPCs also span availability zones, which are the physical data centers in AWS, and the subnets in your VPC reflect that. This allows you to place services in multiple subnets, which means that the physical hardware hosting your service is in different data centers, so it protects your service from an outage when AWS has a problem in one of their data centers. This is critical to understand and utilize to build highly available, fault-tolerant services. And now at some point, you're going to need storage, and there are two common places to store stuff in AWS, EBS and S3. EBS, or the Elastic Block Storage, can be thought of like a physical hard drive that can be attached to your services, and from your perspective, it looks and acts just like the hard drive on your computer. S3, though, is an object store, and it's called that for a good reason. You give it an object, and it keeps it for you. It doesn't really care what the object is. It differs from a file system in the fact that there really isn't a file system or concept of folders, just objects. S3 buckets are commonly used to store the HTML, JavaScript, and CSS for static websites, but they can also be used to store files that you need to download later. You need to be very careful setting up permissions on these. If you leave one publicly exposed, within minutes, you'll be guaranteed to be hosting your very own copy of every type of illegal video on the internet. You should also be familiar with the S3 Glacier service. It's an archiving service for data stored in S3 that allows you to configure rules that will move data from S3 to Glacier based on inactivity. Storing data in Glacier is cheaper, so it saves you money on your AWS bill by archiving data that you aren't using. And take that from a guy who once paid $40,000 for stuff I stored in S3 that I didn't need. Yeah. Anyway, moving on. Most database services in AWS are listed under RDS, or Relational Database Service. Many companies no longer have database administrators, so that means you either have to do the work yourself or pay someone to do it. And that's where RDS comes in. They handle the backups, replication, updates, and the security patches. Another nice feature about RDS is choosing the database engine. You can specify that you want an RDS instance and then tell AWS whether you want that engine to run PostgreSQL, MySQL, MS SQL, or a few other options. There are also a couple of NoSQL or document store database engines available. DynamoDB is Amazon's own proprietary NoSQL data store, and they also have DocumentDB, which is compatible with MongoDB if you're looking for something along those lines. Next, we'll talk about Route 53. It's Amazon's service for managing domain names and DNS. It's pretty straightforward and easy to use and pretty cheap, but I don't recommend it. If you're new to AWS, definitely spend a few minutes getting familiar with it, but then head on over to Cloudflare. Cloudflare is pretty close in cost, it's even easier to use, and it adds a couple of features that you're really going to want. I already mentioned that every script kiddie on the internet has AWS's IP addresses memorized, so it's only a matter of time before someone launches a DDoS attack against you. DDoS is a distributed denial of service, meaning that they flood your servers with so much traffic it brings your site down. This can be triggered by a competitor to your business, someone who didn't like something you said on Twitter, or just someone who's bored and wants to see if they can pull it off. And this is the main reason I like Cloudflare. They detect and handle the DDoS traffic for you and only send the legitimate traffic to your site, meaning that you stay up and running. Now, Cloudflare also has CDN caching. This means you can store assets like images, JavaScript, CSS used by your site out on CDN servers that are physically close to the people using your site. This results in faster download times and the illusion that your site's faster than it really is. Just to be completely transparent though, you can do those things in AWS as well if you build it. But Cloudflare has already built it, so you've got enough work to do already, so let's not do work that's already done. Speaking of which, CloudFront is AWS's service for providing CDN. If this is something you really want to build yourself, or if you have reasons that you can't use Cloudflare, then CloudFront is the service for you. AWS CloudWatch is one of those services from AWS that's multiple services rolled up into one name. So let's start with CloudWatch metrics. As the name implies, you can use this to capture key metrics like CPU utilization, memory, disk space, and observability metrics like API endpoint response times and the number of hits. And with this data being collected, you can set up CloudWatch alarms to notify you when certain thresholds are exceeded. For example, when your API response time exceeds 1,000 milliseconds. You can also use these metrics to trigger auto-scaling. So when that API response time exceeds 1,000 milliseconds, you automatically deploy additional servers or containers to handle the load. And then later, when the response time drops back down, you can deprovision some of those assets so you're not paying for resources that you don't need. And finally, we have CloudWatch logs, which are really useful for troubleshooting, debugging, and observing what is happening in your infrastructure. This is also going to be your primary means for relaying production data back to your development team so that you don't have to give them access to your production servers. And this is another area where I'm going to recommend a non-AWS service. The CloudWatch suite of tools works great, but I find them a little bit cumbersome. Like a lot of AWS tools, all the pieces are there, you just have to assemble them, or you can find a pre-assembled solution, in this case, Datadog. Datadog covers all the things I mentioned above, plus they have pre-built dashboards, recommended alerts, and integrations for tools like PagerDuty to notify you when alert thresholds are exceeded. All right, the next one we're going to talk about is a monster, but it's by far the most important as well as the most difficult to understand, IAM, or Identity and Access Management. So far in this video, we've talked about a lot of services, but how do we manage who can use those services or which services are allowed to talk to each other? Well, IAM is the tool for handling this. It allows you to create users in your AWS account and govern what access those users have using IAM roles and policies. These roles and policies are pretty powerful, and not only do they control the permissions for your users, but you can use them to control the permissions for your services as well. For example, you can define a policy that says your containers for a specific app running on Fargate can talk to a specific RDS instance, but not to anything else. This has obvious benefits to ensuring that a compromised user account is restricted in what they can do, but also a compromised application is restricted in the damage that it can do as well. With that kind of power and flexibility, it's easy to understand why IAM is a challenging topic to master. It's really important that you do, though, so don't get discouraged, and over time, you'll get the hang of it. There's a ton of info available for free over at k9security.io, including the free book, Effective IAM for Amazon Web Services. So check it out, and again, I'll put a link to it down in the description. The last service I want to talk about is kind of the wrapper for everything we've discussed so far. Most AWS docs, demos, and instructional videos will show you how to go to the console and point and click your way to building things on AWS. And when you're just learning about a service, that's fine. I've been using AWS for over a decade, and I still do this whenever I'm exploring. But, and this is a big but, we don't build production infrastructure using point and click. Because let's say you do, and then someone comes along behind you and changes it. How do you know? Or let's just say you need to build something just like something that you've already built. Which buttons did you point and click on? No one knows. And this is where infrastructure as code comes in. What it means is all of the infrastructure services we've talked about in this video get documented as code, and we use that code to build the infrastructure, not the AWS console. So if we need to duplicate it, we have the code showing exactly how we built it. If we suspect that a setting has been changed, we run our code again, and it clobbers any settings that don't match what the code says it should be. If we need to change it, we make a change to our code and deploy it, and the change is forever documented in our code, showing who changed it and why. AWS has a few tools to accomplish this: CloudFormation, Elastic Beanstalk, and OpsWork, and they also have a developer kit as well called CDK, or Cloud Developer Kit, and I don't recommend using any of them. Terraform is the tool you want to use. It knows how to build AWS services, possibly better than AWS itself, Plus, it meets all the conditions we talked about just a minute ago for infrastructure as code. And as a bonus, it also supports Google's platform, GCP, as well as Microsoft's Azure, and it supports Cloudflare and Datadog, two of the other non-AWS platforms I've recommended in this video. Terraform is made by HashiCorp, and they have some amazing learning resources on their website, so that's all I'm going to say about that. One other tool I'll recommend, though, is Pulumi. Pulumi is very similar to Terraform, and as a matter of fact, it even uses Terraform under the hood for some things. The difference between the two is Terraform is very declarative, meaning you write down or declare what the end result should look like. Pulumi is programmatic, so you write a program that uses Pulumi to build your infrastructure. One of the places I like to use Pulumi is when I want the software engineers that I support to do my job for me. Seems reasonable, right? Well, because it's programmatic and available in a common programming languages used today, it's easy for developers to read, understand, and reason about, even if they don't know anything about AWS. This means that you can accidentally teach them DevOps skills without them realizing it. But don't tell them that. It's going to be our little secret, okay? As we start winding this video down, let's talk about how all of these Lego pieces start fitting together to build a scalable application. After all, that is the promise I made in the intro to this video. Scalability refers to your application's ability to perform well at peak utilization while not spending money on resources you don't need at times of low utilization. There are two ways to scale an application, up and out, or they may also be referred to as vertical and horizontal scaling. Scaling up or vertically means adding more resources to your server, such as increasing the amount of memory or the number of CPUs. And this is pretty easy to do in a cloud environment. It's just a matter of changing the settings and restarting your server. Scaling out or horizontally means adding more servers to your application rather than modifying the existing servers. So we may go from 3 servers hosting our application to 6, and then back down to 3 when the peak subsides. In practice, you're going to use both of these approaches. Databases are better suited to scaling up rather than out, and applications are easier to scale out rather than up. Putting your applications behind a load balancer makes it easier to scale out, which is another reason why I strongly recommend that you use them. The DNS name for your load balancer won't change regardless of how many servers you add or remove behind it, meaning that there's no impact to your end users. Scaling out is also the driving factor of why I recommend a container strategy rather than using EC2 instances. Containers are easier to build, they start in seconds, they cost less, and they're disposable when you're done with them. Availability is the other factor we need to consider. Availability means you're able to withstand failures in your environment and still have your application available to your customers. So let's say we have one server hosting our application. When, and note that I said when, not if, it crashes, your application's completely down. A logical progression on this is 2 application servers, right? We just doubled our availability. Well, actually that's wrong too, because what commonly happens is if your backend servers are properly provisioned, they're going to be running at 60 to 70% capacity. Now, when one server crashes, all the traffic goes to that remaining server. And if that server that crashed was at 60% capacity and the remaining server is at 60% capacity, that's 120% capacity on one server. So it's going to crash too. And now we're back to having 0 servers available. So in reality, 3 is the minimum number of servers for a production application. This ensures that we can lose one server and the load it was carrying can be safely redistributed across the remaining 2 servers. Location counts too. If all 3 of those servers are in the same physical data center and that data center goes down, we're still down. To account for this, we need to be aware of regions and availability zones in AWS. Your VPC will be located in one region. A region is just that, a region of the world where stuff is located. For example, US East 1 is in Virginia, and the US East 2 is in the state of Ohio in the US. Within each region are multiple availability zones. And it's easiest to think of an availability zone as a physical data center, though that may not be 100% accurate, but it's a good mental model. So when we build the 3 servers hosting our application, we want to make sure that each server is in a different availability zone to protect us from the impact of a data center going down. Each subnet in your VPC will be in a different availability zone, so that should serve as some guidance in achieving this. And for what it's worth, AWS puts a ton of work in determining where the data centers for each availability zone are located. Each availability zone is on a different power grid with different network connections, different water supply, on a different floodplain, and on different fault lines if that's necessary to ensure that natural disasters won't easily be able to impact multiple availability zones. Now, you may be tempted to put your application across multiple regions, and I'm going to recommend that you don't do that unless you can come up with some pretty compelling reasons that it's worth the extra effort. The most common reason I hear is to better serve customers closer to that region, but it's usually not true when we consider the trade-offs and dig in a little deeper. Let's talk about it. Let's say that the latency we know that the latency from the west coast of the US to the east coast is about 70 milliseconds. But to pull off an application running on both coasts of the US, we need to support multiple regions. We need to route traffic based on geography, which doesn't work as soon as your users add VPNs to the mix. And we either have to replicate data between the regions or rely on data in one region, which puts us right back into that cross-continental hop. This will easily triple the amount of infrastructure you have to support, all to shave 70 milliseconds off of a request time. But consider this. The average response time for most applications is 1,000 milliseconds or more, so we're tripling our efforts and tripling our costs to save 7%. In my experience, spending that same amount of time on improving the performance of your code results in far superior results with less long-term maintenance and costs. The last thing we're going to talk on in this video is security. And here's the reality. If Citibank, Uber, Delta Airlines, Barnes & Nobles, JP Morgan Chase, and Facebook got hacked, you're going to get hacked as well. It's not if, it's when, and your best bet is to build systems that limit the scope of the attack when it happens. So here are some tips in just no particular order and by no means an exhaustive list, just some things that I thought of to get your brain thinking about security. First, avoid using the AWS root account. This is the account that gets created when you create your AWS account. Immediately create an IAM user, give it the necessary permissions, and then change the root password and store that password safe somewhere. For your IAM users, require strong passwords and multi-factor authentication. You also want to avoid putting your API keys directly in code and beware of copy-pasting code online. One of my customers did this once, and within 12 hours, they had a $25,000 AWS bill from someone using those credentials to launch servers and mine Bitcoin using their AWS account. You want to rotate your API keys at least annually. I actually get a lot of pushback on this, and people say, well, what if that key is in use somewhere and it breaks? I always say, well, that's great. We didn't know that before, and now we do, so we can fix it. You can eliminate a lot of the hassle with IAM keys by using IAM roles instead. You can assign permissions to a role, then either assume that role to gain those permissions or run your service with that role so that it gets those permissions without storing keys anywhere. Sometimes you're going to need to access systems remotely, like SSHing to a Linux server, but avoid exposing your SSH port publicly. As I mentioned before, everyone knows AWS's IP addresses, so once hackers see port 22 open, they're just going to beat on it relentlessly until they break it. Instead, use a bastion host, sometimes called a jump host, or build a VPN server. Encrypt all of your data at rest. This means when you save data somewhere, it should be encrypted. At least this way, when it gets hacked, it can't be read. Passwords and credentials should be stored in a system designed for such purposes, like AWS Secrets Manager. And you also want to encrypt your data in transit. This means when data is going from one server to another, it should be doing so over an encrypted channel. This prevents the data from being read, but the transit process itself also prevents a man-in-the-middle attack where you're actually talking to someone different than you think you're talking to. Like I said, we could go on and on about security, and to be honest, it's a never-ending topic. So use this as your starting point and just continue to hone your security skills as you progress in your career. All right, so that's it, right? Ready? Break. Now, seriously, that is a lot to take in, so don't feel like this isn't for you if you now have more questions than you did before you started watching this video. My goal here was just to introduce you to the main topics and give you enough info to start building something for yourself, knowing that you're on the right track and can expand on what you've learned here over time. If you would like the guide that I created for this video, which includes my transcript, the notes, and the links to the reference materials I used to create the video, I can send it to you. And this is probably going to end up as a full course as well, where we build a scalable application in AWS using all the tools and techniques I talked about in this video. So if you want the guide, early access to the course, plus my DevOps Roadmap Career Guide, head over to devopsfordevelopers.io/send it, and I will send it your way. Thanks for watching, and let me know in the comments if you found this video helpful, and I will see you in the next video.